Good evening to all the participants. Is my voice audible to all of you?
Yes, sir, your voice is audible.
Okay. So till now only 29-30 participants have joined. So let's wait 1 or 2 minutes more, then we will start the session. Okay, so let's start the session. So is my screen visible to all of you?
Yes, sir, your screen is visible.
Okay, thank you. So now in this session that we will discuss the first CNN architecture. Uh, First CNN architecture. I should say the first fully connected this convolution architecture. The first fully connected the convolution CNN architecture, and the input is here the MNIST dataset. The dataset that the researcher they have used is MNIST dataset. Okay. So the model name is LeNet-5. And it was introduced in 1998, and the researcher, the name was Jan LeCun. Okay, so this one is a grayscale image. The input image is grayscale image. So grayscale that having the dimension 32 cross 32 cross 1. Okay, so only one image, single. And this MNIST data set. So this data set is a 0 to 9, that is number. Okay, 0 to 9, and the dimension of this was 32 cross 32 cross 1. Clear? So now we need to classify whether the input image the number is 4, or whether the number is 5 or 6 or any number. Okay, in between 0 to 9. So the input is 32 cross 32 cross 1. Now here the filter size is 5. Okay, and number of filter is 6. Number of filter is 6. So now you have to tell me each and every time the two things. First, the dimension of the feature map. Okay, and the trainable parameter. So first you tell me the dimension of this feature map. So First, you tell me the proper this dimension of the filter. So the filter size is 5 and number of filter is equal to 6. So this one is the number of filter that is equal to 6 and filter size is 5. Okay. So now tell me the dimension. Okay, this dimension of the filter and the feature map. Please, right now I cannot see the chat box. Okay, so the dimension of the filter that would be 5 cross 5 cross 1. Okay, and the feature map, the dimension of the feature map that would be 28 cross 28 cross 6. Okay, so as we know the formula that is n minus में f. The formula is n minus में f plus में 1. Okay, so here that is n is 32, f that is a 5 plus a 1. So that is the 28. Okay, so the 28 cross 28 cross 6. Okay, now after this first convolution, then max pooling. Okay, so now we know already the meaning of this max pooling. Okay, the size of this feature map that is 28 cross 28 cross 6. So now after the max pooling, now what would be the size of the output image? The max pooling. Okay, so now here the max pooling where the dimension or the size of the window or filter that is equal to 2 and stride is equal to 2. Clear? So now tell me the size, the dimension of this feature map 1 after this max pool. So now this window size is equal to 2 and this stride is equal to 2. So now that it would be 14 cross 14 cross 6. Correct? So now that 6 that will be the same because pooling does not affect the third channel. This pooling that does not affect the third channel. Okay, fine. So now after this, again, second convolution, okay. Now the size of the is equal to 5 and the number of after this that is a okay where the filter size that is equal to 2 and stride equal to 2. Clear? So now tell me again the dimension of the feature map. So now dimension of the feature map that would be 5 cross 5 cross 16. 5 cross 5 cross 16. Clear? So now do the flatten. Okay, the final the feature map that is one dimension. So if we apply the flatten or the fully connected with a dense layer, flatten, then the number of nodes here that will be 400, isn't it? The number of the node that will be the 400. Okay. So now in the next layer, okay, that you can call as a hidden layer. So number of node in the first hidden layer that was 120. Okay. So now 120. So the researchers that have designed in this way, okay, so that we cannot change here the size of the filter and the number of the filter. So it is the fixed one. Okay. This is the LeNet 5 architecture. So the number of the neurons in the first hidden layer that is 120, and this 400 that is coming after the flatten of this feature map. Okay, and the number of neurons in the second hidden layer that is 84, and the output, the number of neurons that is output in the output that is 10. Okay, that just because of the softmax activation function, because we need to classify the number. Okay. So the output that belongs to which number? So 0 in between 0 to 9. So that is the reason to use the softmax. So the number of the nodes that is at the output side that is equal to 10. Clear? So now the important point is here the learnable parameter, the trainable parameter. Okay. So see, this is the first architecture. Okay, in this session, this LeNet 5. So now in the next session, that we will discuss the this uh, ResNet, okay, InceptionNet. So just to understand the InceptionNet concept of InceptionNet, you have to just first understand the this trainable parameter. So how we can calculate the trainable parameter, the size of the filter, okay, the dimension of the feature map. So you have to understand first all these things. Then only you can understand this feature map. Sorry, the InceptionNet. Okay. So now tell me the learnable or trainable parameter. So now this is the first convolution layer on one. Okay. Now tell me the dimension. Sorry, not dimension. The trainable parameter. So here the trainable parameter. Now anyone please, trainable parameter. Okay, I cannot see the chat box. Let me check. Oh, so here the trainable or learnable parameters that are 0, because here the max pooling or pooling that we use only just to reduce the dimension of the feature map. Okay, so now there would be no filter, okay, that involved here in the this pooling side. So the learnable or trainable parameters that are 0. Fine. Now here in the second convolution, this one. So now learnable or trainable parameter. Yes, anyone? So that is 5 cross 5 cross 6 cross 16. Okay, fine. So now here that is a average pooling. Okay, again the learnable parameter that is 0. Fine. So now here this one is a 400, that is the number of neurons. So 120. So now the learnable or trainable parameter, that is 400 multiplied by 120. Clear? The next one is 120 multiplied by 84. Okay. And the last one is, that is 84 multiplied by 10. So just you count this number. Okay. So that is the first. This one is the first one. This one is the second one. Okay. This is the third one, fourth, and this one is the fifth. So that is a reason to call this LANET 5. Okay. 5 means that is a 5 number of layers. So now here the number of trainable parameter, then 5 cross 5 cross 6. So that is 150. Okay. Now 5 cross 5 cross 6 cross 16. That is equal to 2400. Correct. So now 400 multiplied by 120. That is 48,000. 180 multiplied by 84. Okay. So that is 10,080. And this one is the 840. So now if you add all this one, first is 150, first that is a 150, then 2400, then 48,000, then 10,080, and then 840. Okay, now if you add, so it will be near about 60k parameter, 60,000 parameter, learnable parameter, trainable parameter. Okay, so this one is the architecture of LANET 5. Okay, so if anyone is having any doubt related to this one, hello, any doubt? Okay, so max pooling 14 crores, 14 crores 6. Hmm. So now 14 crores, 14 crores 6, that is the, this one is the size of or dimension of the feature map. Okay, means after this pooling. So 14 crores, 14 crores 6. After this first convolution, 28 cross 28 cross 6. Now max pooling, the window of this pooling, that is equal to 2 and stride is equal to 2. So 14 cross 14 cross 6. Okay. So I hope that it is clear to all of you. Fine. So now the next is AlexNet. Okay. So now here the AlexNet, the researchers that have used the RGB image. Okay. So now 224 cross 224 cross 3. This one is the RGB image. And this model, that AlexNet model, that is trained over the ImageNet dataset. ImageNet dataset. Clear? Okay. So now you see here the filter size is 11, stride is equal to 4, padding is equal to 2. Now tell me the dimension of the feature map. So the dimension of the feature map, that would be 55 cross 55. Okay. Now the number of the filter, that is equal to 96. So here 55 cross 55 cross 96. Clear? Here the size, the dimension of the filter, that would be 11 cross 11 cross. Here this 224 cross 224 cross 3. This one is a fixed size. Okay. This one, that is a fixed size. This is the input image. And it is the RGB one. So 224 cross 224 cross 3. So like this. This 224 like this. One is RGB. Correct? Okay. So now the dimension of the filter, that is 11 cross 11 cross 3. And the dimension of the feature map, that would be 55 256 cross 256 cross 256. How it would be 256? 256. See, so 224 cross 224 cross 3, that is the input image. Filter size is 11, stride is equal to 4, padding is equal to 2. Number of filter is 96. Okay, so the dimension of the filter, that would be 11 cross 11 cross 3. Clear? So now the feature map, the dimension of the feature map, that would be 55 cross 55 cross 96. So up to so far is clear to all of you? Okay, fine. Clear. So now after this, that is a max code. So the formula, that is, see, should I write here the formula in the next page? Probably. Okay. See, the formula, that is n minus my f plus my 1. Okay. The second formula is n minus my f plus my 2p plus my 1. This one is without padding. This one is a with padding. And n minus my f plus my 2p divided by s plus my 1, that is with padding and stride. Clear? So now accordingly you use the formula. So n minus my f plus my 2p divided by s plus my 1. Clear? So now see here, filter size, that is 11. So the formula, that is n minus my f plus my 2p divided by s plus my 1. So if you put n, that is 224, filter size, that is 11, padding, that is 2, s is equal to 4, then plus a 1, so that the value that will come, that is 55 cross 55. And this 96, that is the number of the filter. Now the max volume. Okay. So now max volume. So filter is equal to 3 and stride is equal to 2. So I should say here filter, not filter, that the size of the window of the, at the time of the max cooling, the size of the window, that is 3 cross. Okay, and stride is equal to 2. So if the window size of at the time of the polling, max polling, that is 3 cross 3, and stride is equal to 2, so the dimension of the feature map here, The dimension of the feature map, that would be 27 cross 27 cross 96. Yes or no? Clear? Fine. Now after this, that is again, that is convolution, where the size of the filter is 5 and the number of filter, that is 96. Okay. So now here the dimension of the feature map. Yes. And here the padding, that is same. Padding is same. So now filter size, that is equal to 5. Okay. So now filters size is equal to 5. Okay. So exact size of the filter, that would be 5 cross 96. Okay. So wait here. The number of filter, that is not equal to 96. Number of filter is 256. So number of filter is 256. Okay. So now tell me the dimension of the feature map. So the dimension of the feature map, because padding is same, that is 27 cross 27 cross 256. Clear? Okay. Fine. So now after this, how 256? Okay. So 256, actually this one is the number of filter. Here the number of filter, that is 5 cross 5 cross 96. So 5 cross 5 cross 96. So this one is 5 cross 5 cross 96. This is the 96. Okay, and this is the one filter. So number of filter is 256. Number of filter is 256. Or you can understand like in this way, 5 cross 5. Okay, this 5 cross 5, likewise this one is up to this 96. So this one is a one filter. This is a one filter. And number of filter, like the number of filter, that is 256. Okay, fine. Correct. So now after this, again, that is max pool. Okay, filter, that is 3 and stride is equal to 2. So now the dimension of the feature map, that would be 13 cross 256. Okay, so 13 cross 256. Okay, and the filter, that is the window size of this at the time of this max pole, that is 3 cross 3 and stride is equal to 2. Now after this, again, that is convolution, f is equal to 3. Okay, and here the padding is same. Now the dimension of the feature map, that would be, okay, so the filter is equal to 3. Clear? And the number of filter, that is 384. Okay, so now tell me the dimension of the feature map. So the dimension of the feature map, because padding is same, so that is 13 cross 13 cross 384. Okay, and the filter size, that is 3 cross 256. Clear? Fine. Okay. So now after this, again that is convolution. Okay, convolution. Okay. Same convolution, that is filter size that is equal to 3, that is same padding. Okay, and again that number of the filter, that is 384. So now tell me the dimension of the feature map here. So the dimension of the feature map, that is 13 cross 384. Okay, and the filter dimension, that is 3 cross 384. Okay, so so sorry, this not 384 here. Sorry, my bad. So here this one is uh, the 256 number of it. So here 13 cross 256. 13 cross 256. Clear? So now after this, that is a max pool. Okay, where the window of the filter, that is 3 and stride is equal to 2. Okay, now the feature map, the dimension of the feature map, that would be 6 cross 256. 6 cross 256. Clear? And after this, flatten. Okay, so now you convert this in a one dimension. So if you convert this in a one dimension, so the now it will become 9216. Okay, and the number of neurons in the first hidden layer, this after this flatten, this fully connected layer, okay, the dense layer. So the number of the neurons in the first hidden layer, that is, it was a 4096, and the number of the neurons in the second hidden layer, that is again, that is 4096, and in the output the number of the node, that is 1000, just because of the imaginary data set, because number of class is 1000. Okay, so now we are going to calculate the learnable parameter, again the trainable parameter. Okay, so here in the first this convolution layer, now tell me the number or trainable parameter. So here the trainable parameter that are, let me here in the box, 11 cross 3 cross 96. Okay, I hope this is clear to all of you. So max polling, okay, this here the number of parameter, that is 0. Here in the learnable parameter, trainable parameter, that is equal to, yes, anybody please, learnable parameter. Yes, anyone please. Learnable parameter here at the time of the second convolution layer. Yes, anyone? The images need to be resized. The image actually is this one is the 224 cross 224. So very good. Yes, yes. Not 5 cross 256. 5 cross 96 crores 256. I hope this one is clear to all of you. Okay, so now the max pooling learnable parameter, that is 0. Okay, now here, yes, so now 3 crores 256 crores 384. Very good. Now here, this side, 3 crores 384 crores 256. Okay, correct. So here the max pooling, so that is 0 here. So now this side, 9216 crores 4096 here, 4096 crores 4096, and here at the last, this 4096 crores 1000. Okay, so this one is the first, this one is the second, okay, this one is the third. Oh, I think I forgot to tell you the one. I missed the one convolution layer. Okay, so now see this, after this third convolution layer, that is filter size is 3. Okay, and the number of this filter, that is 384. Again the same, okay, the same number of filter and the same, the size of the filter and number of filter, that are same again in the fourth one. So the learnable and trainable parameter, that would be 3 crores 384 crores 384. Clear? After this, after this, so now it's a 4. Clear? Now after this, the filter size is equal to 3 and the number of filter, that is 256. So now this would be 5. Okay, clear? And now this would be 6. Now this would be 7. Okay, and now this would be 8. So in AlexNet, so number of layer, that would be 8. Okay, so AlexNet. So learnable parameter, trainable parameter, and the dimension of the feature map. I hope this is clear to all of you. If any doubt, any convolution layer, this max pooling, anything is there, please let me know. Okay, fine. Correct. So now the next is, that is VGG 16. So this VGG 16, that is Visual Geometry Group. This one, the name. This one is the Visual Geometry Group. VGG 16 here, that is a number of layer. Okay, so see the average pooling and the max pooling. Okay, so max pooling and average pooling. See here, the meaning of max pooling and average pooling that already that we have covered. The point is where we should use the average pooling and where we should use the this max pooling. So again means it is not fixed. Okay. So you have to use all the time in a one model that max pooling, or you have to use all the time the average pooling, that is it is not fixed. Okay. Now see here in the Lenet, see here that is max pool, and this here that is average pool. Okay, so this one is a fixed architecture. Okay, the question is, it is not mandatory to use all the time max pooling or all the time average pooling. Okay, you can use in place of this max pooling here, you can use the average pooling. Okay, it depends on the application to application, and again it depends on the this performance of a model. Okay, if you get the performance of a model is better, okay, so then you can use the average pool. So max pooling and average pooling, okay, that it depends on the this application to application. It means it is a means the max pooling is not dominate on this average pooling, or average pooling is not dominating to this max pooling. So this depend on the this application. Okay. So now this one is a visual geometry group. So the number of layer here, that is 16. Okay. So now the point is, important one is, wherever convolution used in the VGG16, okay, that means yes, convolution, wherever we use the convolution in this VGG16, the number of layer, this one is the number of layer. Okay, so convolution, it means 3 cross 3 filter size. Okay, stride, that is equal to, that is 1, and padding, that is same. So you have to keep remember this 3 point. Okay, at the time of the convolution. So the point is, wherever the convolution used in this VGG16, we have to keep the filter, that this filter size is fixed. Okay, here the filter size is fixed. Okay, and the max pooling. So here the max pooling, the window of this filter, okay, the size of the filter or the size of the window, that is 2 cross 2. This one is a window size, the 2 cross 2, and stride is equal to 2. Stride is equal to 2. Okay. So now the point is here, this one is a fixed, and this one is also, it is a fixed. Clear? And this VGG also, that is developed on the ImageNet dataset. This ImageNet dataset. Okay, and it was invented in 2015. Clear? Okay, fine. So now let's discuss the architecture of this VGG16. Okay, so now this convolution, just you have to keep in mind this convolution and this max pooling. Okay, fine. So now this one is a VGG16. So here the input is 224 cross 224 cross 3. Okay, so this one is the size of the this input image. Dimension of the input image 224 cross 224 cross 3. Here the convolution is 64, that is multiplied by 2, Clear? So what does it mean? This cone 64 multiplied by 2. So 64 here, the 64 means 64 filter, the number of filter. This one is here, the number of filter is equal to 64. Okay, and multiply by 2 means 2 times they will run. Okay, so after conversion, then apply ReLU, then again do the conversion. Okay, so first convolution, so this one is a image. Okay, this one is a filter. Okay, this one is a feature map. Okay, now apply the ReLU activation function. Clear? Now after apply the ReLU on this feature map, then again just you do the convolution. So this is the convolution. Okay, this one is a cone one, then ReLU, then cone two. Okay, so this is the meaning that multiply by 2, isn't it? Okay, fine. So now the dimension of the feature map, that would be, because padding is same, okay, padding is, you can see here, this one, padding is same, padding is same. So now 224 cross 224 cross 64, then max full. Okay, so the dimension of the feature map, that would be 112 cross 112 cross 64. So the third dimension that would not change just because of the pooling. Okay. So now after this, that is convolution. So convolution 128 multiplied by 2. So here the number of filter is 128. Okay. Okay. And two layer of convolution, that is multiplied by 2, that is two layer of convolution. So two layer of convolution, that is, so the dimension of the feature map, that is 112 cross 112 cross 128. Clear? So now after this, that is again, that is max pole. Okay, so the dimension, that would be 56 cross 56 cross 128. Now after that, this one is a cone 256 multiplied by 3, means 3 layer of convolution. This one is a 3 layer of convolution. Cone 256 means number of the convolution, sorry, number of the filter. The number of filter is 256. So now output, the dimension, that is 56 cross 56 cross 256. Okay, so 3 layer of convolution means, that is convolution, then ReLU, then convolution, then ReLU, and then convolution. That is the meaning of this multiply by 3. Okay, so 56 cross 56 cross 256. Now after this, that is max pooling. Okay, so now dimension, that would 28 cross 28 cross 256. Clear? So now after this, that is cone 512. Okay, multiply by 3. So now the dimension, that would be 28 cross 2 28 cross 512. Clear? Now after this, that is a max pole. So the dimension, that would be 14 cross 512. Clear? Now after this, that is a convolution, that is 512 multiplied by 3 number of layers. So the dimension that will be 14 cross 512. Then max pool. So that is 7 cross 512. Okay. So now after this, that that is a flatten 10th layer. So just you multiply this 7 cross 512. Okay. So now it will be 4096. Correct. So now 4096, the number of node in the first hidden layer, that is 4096, number of node in the second hidden layer, that is 4096, and the number of node in the output layer, that is 1000, just because of the softmax. Okay, and the data set is ImageNet data set. Clear? So now we are going to calculate the learnable parameter, trainable parameter. Okay, so here the trainable or learnable parameter. So learnable parameter, that is again, that is easy. Okay, so that already that we have calculated the learnable parameter in LeNet 5 and LXNet. In fact, CNN also. So now the first one is learnable parameter, that is convolution 64 multiplied by 2. Okay, so yes, tell me the learnable parameter. Here in the convolution, at the time of the convolution, the filter size is 3, that is fixed. Okay, so now you see here, this filter size is fixed. Stride is equal to 1, padding is same. So now 3 cross 3 cross 3 cross 64. Clear? So that is the first one. Now max polling, okay, again that is 0. So first you calculate the number of layer. First you calculate the number of layer. So now here, that is number of layer, that is 2. Okay, again that is 2, 4, that is 3, 7, that is 3, 10, and 3, 13. Okay, 13. Then this will be 14. 4096 multiplied by 4096. Okay, this one is the 14. Here 4096 multiplied by 4096, that is 15. And this one is last, that is 16. 4096 multiplied by 1000. So now number of layer is 16 in the BGT 16. Okay. So now the trainable parameter or learnable parameter. So here the learnable parameter, that is 3 cross 3 cross 3 cross 64. Clear? Now this second, so this 3 cross 3 cross 3 cross 64. Okay. Now in the second, this convolution layer, that is 3 cross 3. Okay. So now you tell me the dimension, not dimension, sorry, the learnable parameter. White color. Yes. 3 cross 3 cross 64 cross 64. Okay. So max pooling, that is 0. Now here the convolution second multiplied by 2. So now 3 cross 3 cross 64 cross 128. Now 3 cross 3 cross 128 cross 128. Okay, so max pool, that is 0. Now convolution 256 multiplied by 3. So here, let me write here this side, this side. Yes. So 3 cross 128 cross 256. Okay, clear? So now after that 3 cross 256 multiplied by 256. Again 3 cross 256 multiplied by 256. So max pooling, that is 0. And this convolution 512 multiplied by 3. Okay, here. So now 3 cross 256 multiplied by 512. So 3 cross 512 multiplied by 512, and 3 cross 512 multiplied by 512. Okay, so now max pole, that is equal to 0. So now convolution 512 multiplied by 3. So now 3 cross 512 multiplied by 512. 3 cross 512 multiplied by 512, and 3 cross 512 multiplied by 512. Clear? And this max pole, that is equal to 0 again. Okay, now this one is a 14, this one is a 15, this one is a 16. So in total, okay, if you calculate the total learnable parameter, okay, so now just you calculate the total, maybe that is 60 million. Okay, so 60 million, that is I think 120 million learnable parameter. So here 13 this convolution layer, okay, 5 max pool here, and that is 3, that is a kind of dense layer. So this model actually it is popular because this one is a inbuilt in Keras package. So no need to build from scratch. So you just call a function VGG16. Okay. So you don't need to develop the model from the scratch. Okay. Just you call a function that is VGG16. So I hope this VGG16 is clear to all of you. And VGG is 19. Okay, so VGG 19, that is 3 more layers that would be okay there in the VGG 19. So likewise, I hope now just you do by yourself VGG 19. Okay, this one is a VGG 16. So now I think you know how to calculate the dimension of the feature map, how to calculate the learnable parameter, trainable parameter. Now this will be easy for you the VGG 19, I think. Okay, so now you do by yourself the learnable, trainable parameter. Okay, fine. So is there any doubt? So how comes this 4096? This 4096. Wait, exact question is how come in 15 layer 4096? So now the second question is, can we use 256? 256? Okay, fine. So let me answer. Okay. So now this 4096. Okay, the 15. So this 4096, this one is that is coming after the flattened. Okay, 7 cross 7 cross 512. Okay, let me explain this here. So 7 cross 7 cross 512. Okay. So that is 4096. Clear? So 4096 means that is 409 after the second number of nodes. In the second is 409 nodes. In the first hidden layer, the number of nodes that is 40 is number of nodes. In first and this is the hidden layer. So now you have this one. Layer. So now that is this 4096, that is the number of node in the first hidden layer, and the number of node in the second hidden layer, that is again that is 4096. So 4096. So now in 15 4096 multiply by 4096. So likewise this again you do the same way like this. Clear? And the last one, that is a 1000, just because of the ImageNet data set. So 4096 multiplied by 1000. Okay. So now the second question, the size of the this input image, that is 224 cross 224 cross 3. So, so now this size that it was in the original paper. Okay. So that I use the same dimension, same architecture. Okay. So now original paper, this one, this VGG 16. Okay. So now I think this VGG 16, that it was invented in uh, 2004. Okay. So I can send you the original paper. Okay. So maybe, so the title I'm writing here, so very deep convolutional network for large scale image recognition. Okay, so I will share this original, this paper. Okay, this one is the title of this original paper. And yes, so now I can recall the number of trainable parameter, that is 138 million parameter. Okay. So now I will share this paper, this LANET paper, the AlexNet, okay, and this VGG16. So all three papers that I will share, okay, on the Canvas, this portal. So you please request to just please go through all these three papers, okay. And if you are having any doubt related to the paper, then you may ask in the next session, okay, maybe in the next other day. Okay, so in the next session, after this 15 minutes that I will take, so in the next session that we will discuss the ResNet and the InceptionNet model. Okay, so now let's take the 10-minute break. Okay, so 6:15 that I will start the next session on the ResNet and ImageNet model. Okay, so if you have any doubt, then you please write in the chat box. Otherwise, we will start the session after 10 minutes.